numbers greater than or equal to 10. We're going to write it in set builder notation. First, I have to tell you the symbol for the real numbers. So I think I went over some symbols last time. I may not have done real numbers. The real numbers is this sort of weird script looking R. So it's like a capital R with two vertical lines there. So that's the set of real numbers. And I think I described the set of natural numbers and integers last time, but maybe I didn't describe this one. So that's the set of real numbers there. That's the symbol we'll use. Okay, so first off, they tell us to let the set be M. So I know M is going to be the name of my set. Then I'm going to say equals, and then I'm going to have my curly brackets opening. Okay, now since I'm writing it in set builder notation, I need to start off with just some arbitrary element of the set, not an actual item in the set, just a name for some arbitrary element in the set. Usually it's like X, or you could use the lowercase version of whatever the name of your set is. So I could say like lowercase m. I'll just say X though. I'll just say X. And then you put a bar. That vertical bar is read as such that. So what this means, well, I'll tell you what, I'll write how you read this after we get the latter part here. So this part here is actually going to describe how you get into the set M. How you get into the set M. And there's two things that get you into the set M. First of all, X has to be a real number. So how do I describe that? I say X. Remember, this symbol means in, so X is in. So it's, I'll blow it up here, this, so in case you can't see it, that symbol means in. So X is in the real numbers. That's the first thing that gets you into this set. And then if there's more than one thing that gets you into the set, you separate them by commas. And the second thing that gets you into the set is you have to be, or the X has to be greater than or equal to 10. So I literally just write X greater than or equal to 10. And then close the brackets. Okay. So there's an example of writing a set in set builder notation given just a word description, or maybe even a verbal description of the set. Okay, so let me write down how you would read this just to make that clear. M is, so far M equals M is, and then the set. So the set, why am I saying the set? Well, that's what these curly brackets tell me. So M is, and then the set is coming from the curly brackets of elements X, which is just coming from this X, right? Elements X, such that, now I'm going to run out of room drawing my arrows, but the such that is the bar, such that, maybe I can go around this way. I know what I'll do. Such that X is in the real numbers. X is in the real numbers, so that's this part. And is going to be that comma. And now I know you don't have all these colors for your notes, so maybe you can find a better way to write this down. And X is greater than or equal to 10. X is greater than or equal to 10. Okay, so that's the set builder notation completely broken down there. So now I want to do an example where we go backwards, well, or rather where we go from set builder notation to roster notation, which is probably the simplest way to list a set. Now, could we do this one in roster notation? Well, no, because first of all, you can't list real numbers in roster notation. There's just too many of them. And second of all, the set's going to be infinite, even if it wasn't in the real numbers, because it's saying numbers bigger than 10. There are infinitely many numbers bigger than 10. So let's do example 5. And let's list a set in roster notation. So let me get back to the problem I wanted to do. Okay. Write the set using roster notation. B is the set of all elements X such that X is greater than or equal to 10 and X is less than or equal to 28. And so we can just say and. Sometimes you can use a comma, you can put the word and, it doesn't matter. X is a multiple of, let's say, 4. Okay. So I want to write this set using roster notation. So this is set builder notation, and remember, roster notation means like in a list, in a roster, in a list. So now there's not going to be any X. I'm literally going to write elements of this set. Okay, so the first one is a 10. Is 10 in the set? Well, according to this part, yes, 10 is in the set, but over here, I want X to be a multiple of 4, but 10 is not a multiple of 4. Okay, and in fact, I don't need to consider any odd numbers because I know odd numbers aren't multiples of 4 either. So what's the first multiple of 4? It's going to be 12. The next one will be 16. So now I'm just going to start thinking of multiples of 4, and I'm going to be careful not to go beyond this 28. So 16, 20, 24, and then is 28 in the set? 28 is a multiple of 4, but according to the inequality, is 28 in the set? And the answer is yes, because of the little or equal to part, right? It says X is less than or equal to 28, so 28 is included here. So these are two different ways to write the exact same set. This is set builder notation, and this is roster notation. Just two different ways to write the exact same set. Okay, so we've talked about representing sets. We're still in 2.1. We have a few more things to talk about here. The next thing I want to talk about is a couple of special sets. One is called the empty set. This is basically like defining what 0 is in sets. So the empty set, or null set, you may see it that way too, null set, N-U-L-L for null, null set. And it's denoted by, well, I'll say it this way, is the set that contains no elements. No elements. And we denote it by sort of a 0 with a slash through it like that. We denote it by that symbol there. So as a quick example, the set A of, let's say, elements A such that A is in the natural numbers. So that's the natural numbers. Okay, so the set capital A such that is equal to the set of elements A such that A is a natural number, which remember natural numbers are 1, 2, 3, 4, 5, etc. And A is less than 0. But these are like contradictory, right? So what's in this set? Well, nothing is in this set. A is empty because of the way I constructed it. So A, what do we say, is equal to the empty set. There's nothing in there. No elements in the set. Okay. So that it's a special set. It'll come up. It'll come up a few times, especially in the next section. It's kind of a part of a technicality of a definition of subsets. We'll talk about that. So it comes up. It's an important set. It's kind of like the concept of zero in sets. So it's important to define. There's really nothing else to it here. If you understand, if I say what's the empty set and you say it's a set that contains nothing, no elements, then you've got it. That's all you really need to worry about here. All right. So I know I'm not like engaging class this time, but I really want to make sure I get a bit further today. So I'm going to keep right on moving through. Let's talk about another special set called the universal set. So what is this universal set? It is the set of all elements, this is from the text, by the way, I'm still following the text, being considered for some context problem for any particular situation. Is called the universal set, and it's denoted by a capital U. Okay. So a universal set, what is the universal set? Well, it depends on the context of the problem. So let's see if I've done any examples. So for instance, with the example 4 I did earlier, with m being the set of real numbers greater than or equal to 10, the universal set probably would be the real numbers, the set that m is living inside. Okay. Whereas here, for this example I gave of an empty set, like a special construction here to build an empty set, it's kind of up in the air whether it is the natural numbers or not. If it's ever not clear what the universal set is, it will be explicitly defined. Sometimes it's like in an example we're going to see later, it's like the set of all English alphabet letters. That might be your universal set. If the elements you're dealing with are letters, then the universal set is the set of all English letters. So it depends on the context. Another thing I want to say just real quick about the way it's denoted, you're going to want to write your capital U this way. The book writes it without a little tail, but we're going to have a symbol later that looks very much like a capital U without a tail. So whenever you're writing your universal sets, your capital U, just put a tail on it so you know, because later we're going to have this symbol, which will mean something, and that definitely looks like a capital U if you don't have a tail on it. So that's just a small note there about denoting the universal set. Okay. Another quick definition, and I'm throwing these definitions out, but what I'm going to do is define them and then we'll work examples. And these two definitions, they come in pairs here. So the complement of a set A, so we'll say of A, consists of the elements in a given universal set. So like I said, the universal set will be given in a given universal set that are not in A. And we denote it, so it's like the opposite of A. It's denoted by A with a little tick mark up in the corner. There are tons of different ways to denote a complement, but this book and our homework and the exams are the A complement's going to be that little A with a tick mark up in the corner. Okay, so let me give you an example. All right. An example of a complement. So I believe we're on example 6. So you see this complement definitely relies on what the universal set is. All right, example 6. Let's say let U equal, let's see what I want to do here. Let's say let U equal the set of all elements X such that X is an English alphabet letter. Okay, and let A equal the letters A, B, C, D, E, F. We want to find a complement. All right, so I'll give you a second to think about that. Okay, I'm gonna start calling on people to see if you can help me build this A complement. But first, let me say this. The definition of a complement, so A complement, says it should be all the elements that are in the universal set, so English alphabet letters, that are not in the original set A. So, Chastity, what would the first letter you would list? What would the first letter be in your list of A complement?
So it would not be A, right? So
Right.
B, maybe?
But B is in the set A here.
Oh.
All the way up to F, right?
Okay.
So what's the first letter that's not in A?
G.
G.
Yes, G. Yep, thank you. G is the first letter that's not in A. And then we would have what else isn't in A that is in the universal set. We have H, I, basically the rest of the alphabet. P, Q, R, S, T, U, V, W, X, Y, Z. Okay, just quickly listing them there. Okay, so let's look back at the definition, make sure this makes sense. The complement of A is all the elements in the universal set that are not in the original set A. Okay, so basically you list the entire universal set, but you subtract out all of these elements. And I just chose the first 6 letters of the alphabet to be an A, so the last 20 letters need to be an A prime. So there should be 20 here because what is the cardinal number? In other words, how many elements are in the set U? There should be 26. So that means the cardinal number of A, if it's 6, then the cardinal number of A prime should be 20, so there are no shared elements between A and A prime. They're opposites of each other. Okay, cool. So let's see, let's do another example of complement. I gotta find a good one. Trying to use your homework. All right, example 7. Let's do a simple one. Let's say the numbers 1, 2, 3, just up to 10 for. So just natural or whole numbers up to 10. So that's our universal set. This is the world that this problem is living in. And then let's let T equal 1, 6, and 9, and S equal 6 and 3, and R, so the set R, not real numbers, just some name for a set, just be the element 5. Okay, let's find T complement. Let's call that part A, find T complement. Okay, so we're looking for all the elements that are in the universal set, which is 1 through 10, that are not in T, So first number is not going to be a 1, right? It's going to be a 2 because 1 is in T, so I don't want to include that. Also, 3 will be in there, 4 and 5, but not 6, right? Not 6. 7 will be in there, 8 will be in there, not 9 because 9 is in T, and then finally 10. So did T prime have anything to do with S and R? No. T prime has nothing to do with other sets. T prime has everything to do with the universal set and the original set T. So what about find R prime? Find R prime. So there are 10 elements in U and only 1 element in R. So let's see. Sierra, how would you describe the set R prime? Or R complement, rather?
It'd be 1, 2, 3, 4, 6, 7, 8, 9, 10.
Yep, so everything but 5. Good. 7, 8, 9, 10. That's right. That's right. Good. So that's the concept of a complement. Complement we'll actually keep talking about in the next section when we start talking about Venn diagrams, because then we'll have more opportunity for examples of complement. And in fact, this is where section 2.1 ends. So now let's move on to section 2.2. Subsets and Venn diagrams. Good. Subsets and Venn diagrams. Okay, so in this section, we're going to talk about another way to compare sets. So last time we were comparing sets with the symbols equals and then the little squiggly for equality versus equivalence, right? We talked about 2 ways to compare sets. 2 sets are equal if they contain the exact same units, and we use the equal sign for that. And 2 sets are equivalent if they have the same cardinal number, and we use that little squiggly line last time to denote that. So we pretty much discussed that as much as we need to. So now with this subset idea, this is going to give us a new way to compare sets, to say whether one set is contained in another set. And the Venn diagram thing, that's just a picture that's really going to help us understand this notion of subsets. So the book starts off with a definition of Venn diagram, I suppose. I suppose I can do that too. A Venn diagram is a way to visualize some relationship, let's say the relationship between sets. The sets are represented by circles or ovals, and the universal set is represented by a rectangle. So you've probably seen a Venn diagram before. It's like you might have seen two circles with some overlap between them, but really a Venn diagram should also contain a rectangle, which will denote the universal set. So you'll usually see a rectangle with a little U in the corner. That's to denote that everything that's happening in this problem is contained in this rectangle in this universal set. And then you might have two sets in here. And for now, let's just draw them not intersecting. So let's just pretend that they don't have anything in common. There's other, obviously they can intersect and one can be completely contained in the other. There's all sorts of different ways these can be related to one another. So this is just some example of a Venn diagram with two sets, A and B given. And by the way, it's called a Venn diagram. It's just the dude who named it, who created these. His last name is Venn. That's why they're called Venn diagrams. All right. So let's go to an example. Let's get straight into an example using a Venn diagram. Okay, so this is example 1 from the text. We're going to let U be, again, the set of English alphabet letters. So we'll say the way they write it is X such that X is in, and then they say English alphabet. So that's a little less than formal the way they're doing that, but it's okay. We know what they mean. X is like all the alphabet letters, the 26 English alphabet letters. And by the way, we are pointing out English because obviously there's more than one alphabet. All right. In fact, we might even use another alphabet. In math, we use the Greek alphabet a lot. Okay. Here is our picture with the sets S, T, and V inside of our universal set. The set S contains the letters K, A, and lowercase s. And I'm going to name them with a blue marker just so we know that the letter in here is not an alphabet letter. So that's the name of the set, capital S. And then we have T over here, which contains the letters T, J, M, and D. So this is the set T. And then the set V down here contains the letters E, C, and P. All right. Real quick, let me just list these, or actually, no, I'll have you do that as an exercise. What's that? Oh, okay. Oh, yes, there's a question. Is it Aliceel? Is that what you go by?
Yeah, that's my last name. You can call
Okay.
me like that.
Oh, I'm sorry. Okay, Yusuf. Okay.
I just had a question. Why there is 3 letters, S and T and V,
Those are the name of the sets.
but they're not mentioned on the question?
What's that?
But they're not mentioned on the question specifically.
Well, I haven't finished writing the question yet.
Okay. My bad.
Yep. So the first one will be list the elements. List the elements of the sets S, T, and V. There we go. Now they are in the context of the problem. Oh, in roster form. Let me be specific here. In roster form. In roster form. List the elements of the sets S, T, and V in roster form. So the set S in roster form is just those 3 letters, K, A, and S. And if you like, you can list them in alphabetical form. Doesn't matter. T will be the set with the letters T, J, M, and D. And V is the set E, C, P. Okay, so that's all there is. Listing the elements of the sets in roster form, you just list them out. Now, keep in mind, all of these are still in the universal set. They've just been organized into these three little distinct bubbles. So all of these are still in the universal set. Okay. I'm going to follow through the book's example here. The problems they give. They say find the cardinal number of S, the cardinal number of T, and the cardinal number of V. Okay. So remember the cardinal numbers are just the number of elements in a set. So cardinal number of S is 3. The cardinal number of T is 4, and the cardinal number of V is also 3. And do you have to list them in roster notation to be able to see that? Well, no, because you have a picture of the sets. Well, you have a picture of the sets here with the elements listed out. So, but it can help to list them in roster form, I suppose. In this particular problem, there's no real advantage to writing them this way. It's just a good, it's just a good exercise. All right. So what if I said find T complement? I'll switch to going back to red for this.
Is it okay when you get a chance if you go back to A and B of the last ones? Thank
Yeah,
you.
don't forget that if you miss anything that this is being recorded too.
Okay. Okay.
Yeah. But here you go.
Thank you.
Mhm.
Okay, I'm good.
Okay. Oops. Okay. There we go. Okay, so let's say we want to find T complement. So we consider the universal set is the set of all English alphabet letters. And then the set T just has these 4 elements. So what I'm going to do for T complement is I'm just going to list the entire alphabet, but subtracting T, J, M, and D. So this will be a pretty long list here. I'll probably stack it. So we'll start off with A, B, C. Not going to write D because D is in there. A, B, C, D, okay, and then E, F, G, H, I, not J, right? J is in there. K, L, N, not M, right? N, because M is in that set. Okay, hopefully you're getting it at this point because we already talked about complements. So oh, whoops, I skipped Y. There we go. All right, there we go. There is T complement. So notice I didn't even really consider the set S and the set V in this problem because they're not relevant. If I'm looking for T complement, I only need to consider the universal set and the set T itself. Okay, and just as a review of those equality versus equal versus equivalent ideas, this last problem says, is S equal to V? Is S equivalent to V? Remember, those are 2 different ideas. So is S equal to V? Well, to be equal, we need the sets to have exactly the same elements. So we can say no for the first part, no, because they do not contain the exact same elements. Okay, what about is S equivalent to V? Well, S has 3 elements, so remember when we're talking about equivalence, this little symbol, we're looking at number of elements. Well, this has 3 and this has 3. They have the same number of elements. They have the same cardinal number. So yes, S is equivalent to V. Why? Because they have the same number of elements. Okay. Proper subsets. Okay. Let's go to another example. This will be less involved, like not as much writing of particular elements. What I'm going to do is just make sure you understand different ways that Venn diagrams can look, how different sets can be related to one another. All right, let's let you
Can't see what you're writing.
Did the camera turn off? Okay, let U consist of all, let's say, baked goods. Let U consist of all baked goods. So anything that can be baked, cakes, pies, whatever. All baked goods. Okay. So that could be like, we could spend all day discussing, you know, different things that could be in U, but I'm being consistently a little vague about it, right? So we don't need to list it all out. Okay. Let's draw a Venn diagram that represents the relationship between the sets of, or well, let me say the set of, let me think for a moment. Oh, gotcha. Okay. The set of cakes. So that's one set, and the set of chocolate cakes. So this is a lot more vague than the last example, right? The last example, you could have listed out the universal set because it's English letters, and the other sets I gave had like particular elements in there. You could literally list them out in raster notation. But here, this is a little bit more up in the air, right? So, and that's on purpose. That's on purpose. And I didn't even give you letter names for these sets. Well, except for the universal set, obviously. But I didn't even give you letter names for the other two sets. So that means when you draw your Venn diagram, you can just write literally the word cakes and then chocolate cakes on your two sets. So what is it going to look like? So we know a Venn diagram should always start, well, let me draw it in red here. Venn diagram should always start with the universal set. So a rectangle, this is the set of all baked goods. All right. Now I know I'm going to have two circles in here, but the question is, you know, are they distinct? Are they overlapping a little bit? Or is one completely contained in the other? And if one is completely contained in the other, which one is the outer set? Which one is the inner set? So it will be, now clearly they're not distinct, right? If a set, if a cake is a chocolate cake, then it is a cake, right? So they are going to be overlapping, and in fact they'll be of this relationship down here where one is completely contained in the other. Let's see, I'm going to use a different color just to emphasize here. Okay, Oh. And I'm just using ovals because, well, you can use ovals or circles. It doesn't really matter. All right. So what is the blue set going to be? So this is coming up to an important concept here. So Aja, what do you think the blue set would be? Would it be the more vague cakes or would it be chocolate cakes?
I'm thinking that it would be the more vague cakes.
Right, because it's the broader category, right? That's good. That's good. This would be cakes. Because there are things that are cakes that are not chocolate, right? You could have like, I don't know, like a vanilla cake or something, right? You know, or a carrot cake. So this is the broader set. It's the more general set. It's not as exclusive of a club, whereas chocolate cakes is. And if you are a chocolate cake, then you are surely in the category of cakes, right? This set is completely contained in the other set. So this is, I'm going to run out of room, but I'm going to say that's chocolate cakes. Chocolate cakes. Completely contained in the other. Okay. I'm glancing through your homework to see if they give any weird examples like this. I don't see any, so I think we're good. Okay, let me make the point here. The point is chocolate cakes. Let me say this, all chocolate cakes. The point is all chocolate cakes are cakes. Somebody needs to mute themselves. Thank you. Okay, all chocolate cakes are cakes, but not all cakes are, not all cakes are chocolate cakes. So one is contained in the other, but not the other way around. All right. So one is completely contained in the other. Okay. I'm just sorry, I'm glancing through these. No, okay, good, we're good. Let's go to the next definition, which is a subset. So I'm going to go a little bit further, and then what I'm going to do is I'm actually going to open a Hawks assignment and show you how to do your Hawks assignment, just in case there was any questions about how that works. So let's define a subset, which I've been alluding to in this last example. I haven't said the word subset, but here we go. Here it is. If A and B are sets, okay, sure, A and B are sets. B is a subset of A if every element of B is also an element of A. In other words, so I mean, that's correct. I don't really like, if I said it a little bit more in like colloquial terms, in other words, B is completely contained in A. And it's denoted by this symbol. So it's like a sideways, it's like a C with a line under it, like an elongated C, like that. That means subset. So we would read this B as a subset of A. So in our last example, chocolate cakes, which I didn't name it as a letter, so I'll just write it as a word. Chocolate cakes were a subset of the broader category of cakes. All right. Okay. Let's just do another quick example, just a quick example. Let U be the numbers 1, 2, 3, similar to that example we had earlier. And let's let capital X be the set 1, 2, 3. Whoops. Well, let's let X be the set 1, 2, 3. And let Y be the set 2. And let's let capital Z be the set 2, 4, and 6. So what can I say about these sets, these three sets in relation to one another? Are they subsets of one another? What can we say here? First of all, note that they should all be subsets of the universal set, right? That's the point of a universal set, is the universal set should contain every other set that's going on in the problem. So of course, every set here is a subset of the universal set. What we can say here is that in fact, Y is a subset of X because Y only contains the element 2 and the element 2 is contained in X. So we can say Y, capital Y, is a subset of X, but not the other way around, right? X is not a subset of Y. So Y would be completely contained in X. Also, Y is a subset of Z, but not the other way around. And that's all we can really say here. While Z and X do share a common element of 2, they are not subsets of one another. Because X contains things that Z does not, and vice versa. So all we can say, given these three sets, is that Y is a subset of both X and Z, because both X and Z contain the element 2, which is all that Y contains. Y is completely contained in X and completely contained in Z. Okay. Well, I'll leave that there in case you need it. I'm going to move on to the next definition. So first I want to make a note. The definition of subset allows for a strange technicality, which is that any set is a subset of itself. So for instance, if I take the set Y up here, consider the set Y, which is equal to just the number 2 in its set. If I said Y is a subset of Y, is this a true statement? That's what I'm claiming, right? Any set can be a subset of itself. Is this true? Yes, it is, because the definition of subset says if A and B are sets, blah, blah, blah. Basically, the set should be completely contained in the other set. But Y completely contains itself, right? It's just like a little technicality. It's kind of meaningless almost, right? but it is a technicality. Yes, any set is a subset of itself. So given any set, you can say, you know, A is a subset of A, or in this case, Y is a subset of Y. I don't even have to define the set for you. I can just say, given some arbitrary set A is a subset of A. All right. So what we want is we want to get rid of that kind of weird technicality by introducing a stricter definition called proper subset. Proper subset. When B is a subset of A, okay, so we're starting off with B being a subset of A, and A contains at least, I don't like this definition either. I'll give you a better version, but I'm still gonna, just for completeness, I'll write it down. One element contains at least one element that is not in B we say B is a proper subset of A. In other words, you can think of A is, I'm going to put it in quotes, larger than B. And by the way, we denote this very similarly to subset, except it doesn't have the line under it. So it's just this symbol. B is a proper subset of A. So within the definition of subset, it allows for this technicality where you can say a set is a subset of itself, but this gets rid of that technicality. A set is not a proper subset of itself. So really, when you think of subset, your intuitive, like based off of what we worked on, your intuitive definition where one set is completely contained in the other and they're not the same, like one is literally smaller than the other, that's what proper subset is really getting to. So we have two separate definitions, with subset being a more vague definition that allows for a set to be a subset of itself, and then proper subset, which does not allow for that. It's very similar. There's an analogy, especially even with the symbols. It's analogous to this idea. If I'm comparing numbers, not comparing sets, but comparing numbers, I can say 3 is less than or equal to 3, right? That symbol allows for that. It's weird, but I mean, technically it's right because of the or equal to thing. But if I wanted to say 3 is less than 3, that's where, we get into some trouble. So I can say 3 is less than 4, right? So this is kind of like a subset where it allows for this number to be, or a subset to be a subset of itself. But if you want a proper subset, then the other subset has to be bigger. Has to contain at least one thing that the other one doesn't. So that means back here, where is it? Oh, I lost it. Where I defined the set Y. Oh, come on, there it is. X, Y, and Z back here. I could technically say Y is a proper subset of X because Y is completely contained in X, and I can make the same argument about Z as well. So Y is actually a proper subset of X, and Y is a proper subset of Z. All right, so now I'm going to show you how Hawks works real quick. We're not done with 2.2. We still have a few more things to talk about, so we'll finish that next time. So now I want to share my screen. Yes, question?
So what's to tell when to call one a proper subset and when it just be a regular subset if it has the same elements in it?
Right, yes. So here's an example. Let me use these sets real quick. Actually, let me save your question. Let me show everyone Hawks real quick, and then I'll come back to you.
That's fine.
All right. Let me go here. All right. This is not. Come on. There we go. Okay. So when you're in Hawks, let me back up. Let me go. You're in our Canvas page, just real quick in case you don't know how to get into Hawks. You click this little Hawks Learning Single Sign-On button. Should be no problem. I think everyone's already been in Hawks. And then here is where you'll find your assignments. Now, you don't see 2.1 and 2.2 here for me because I already did them just to look through them. So I'm going to have to go through here and click that button, scroll. Okay, there we go. So when you click an assignment, it brings you to this page. This will take you to the textbook and some, I believe, some videos in there for this particular section, which is nice. I mean, if you need extra practice or extra time to learn the material. Then you have this, which is where you can practice the problems. And then you have Certify, which is where you actually get credit for the problem. So once you do Certify, you can only do it once. And built in, there's some things to let you, it has some wiggle room for errors. Like if you miss one or two, then it's fine. It'll let you try a different problem and stuff like that. But if you're not sure, if you're really confident in the material, you can go straight to Certify. If you're not, maybe you'll want to try Practice first. So when you do Certify, it'll drop you into something like this. And then, so for instance, this one says, is P equal to Q? It gives me two sets with the P has 5 vegetables in it and Q is the set of all vegetables. So I could say, no, these sets are not equal because Q is definitely going to contain more stuff in it, right? Because there are more than just 5 vegetables. And so you just proceed, you get one right, you just hit OK. So this one says, again, is P equal to Q? And if we look, we will say that these are equal, just in a different order. So I could say, yes, they contain the exact same elements in a different order. But let's say I wasn't sure and I picked yes because they have the same number of elements. That would be incorrect because that would be talking about the other type of comparison we have for sets equivalents. But let's see what happens. So I click. It'll say your answer is incorrect. So you have you can try a similar question, or you can accept a strike. So for each set of problems, depending on how many there are, you're going to have a certain number of strikes. So I can accept the strike and just say, I'm just not going to worry about that problem and move on, or I can try a similar question. Okay, so that's how Hawks. This Certify, doing all of these problems in each one of these lessons, Certify, is how you get points. This is how you literally complete the homework assignments. This is how you get the points for the assignments. All right, that's it. You guys are good to go. You can stick around if you have questions. Okay, so that was Oliver, I think. Yes.